12 millennia. That's how long Hale-Gubi volcano had been sleeping when it woke up screaming on November the 23rd, 2025. The last time it erupted, mammoths still walked the earth, and humans were just inventing agriculture. What changed? 3 weeks earlier, interstellar visitor 3I-ATLAS did something impossible near the Sun, triggering a solar storm so powerful it could have been a weapon. Now that same comet is heading toward Earth, and volcanoes across multiple continents are stirring like something poked them all at once. Tonight we're investigating the theory that sounds like science fiction, but might be science fact. That space isn't empty, that electricity connects everything, and that we're all living inside a circuit we didn't know existed. Stay until the end to discover what happens when the comet gets even closer. If this mystery continues to have you hooked the way it has me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and what you think about this new development. Part 1. The weak Earth got louder. Something changed in late November 2025. The planet started speaking in a language we thought we had forgotten, or maybe never knew at all. Volcanoes that had slept for 12,000 years suddenly exploded. Earthquakes rippled across continents that share no tectonic connection. The sun threw tantrums we couldn't predict. And floating through all of it, silent and strange, was an object from beyond our solar system that shouldn't behave the way it does. Let me paint you a picture of that week. On November 23rd, 2025, a volcano called Hale-Gubi in Ethiopia woke up. This wasn't some temperamental mountain that grumbles every few decades. This thing had been dead since the end of the last ice age, back when mammoths still walked the earth, and humans were just figuring out agriculture. For 12 millennia, it sat there like a stone monument to geological peace. Then, without warning, it detonated. Ash plumes reached 10 kilometers into the atmosphere. The explosion was so violent that ash fell across the Red Sea, dusting Saudi Arabia in volcanic debris. Livestock died, villages evacuated, the sky turned grey. Hale-Gubi wasn't alone. Around that same 72-hour window, volcanoes across the planet started acting up. Indonesia reported unusual activity at multiple sites. Kamchatka's volcanic arc, always active but predictable, suddenly became erratic. Hawaii's Kilauea, which had been relatively calm, began showing fresh seismic tremors and renewed lava flows. Mexico, Colombia, Alaska, all reporting heightened volcanic signatures within days of each other. These aren't connected systems. They sit on different tectonic plates, separated by thousands of kilometers of crust and ocean. Yet they all decided to speak at once. The earthquakes came next. Or maybe they came first, depending on which seismograph you believe. Small to moderate quakes clustered near many of these eruption sites. Nothing individually catastrophic, but the pattern was undeniable. Earth was ringing like a bell someone had struck with increasing force. Seismologists started comparing notes and realized something uncomfortable. The statistical probability of this many independent volcanic and seismic events, clustering in such a narrow time window, across such diverse geological zones, approaches astronomical improbability. Imagine if every person with the last name Smith in different cities around the world all sneezed at the exact same second. Would you call that coincidence? Now rewind the clock about 3 weeks. On October 29th to 30th, 2025, an interstellar comet designated C/2025 S1, better known as 3I-ATLAS, reached its closest point to the Sun. Perihelion, we call it, the moment when a comet's orbit brings it nearest to our star. For 3I-ATLAS, that distance was about 1.4 astronomical units, or roughly 210 million kilometers. That's actually outside Earth's orbit, farther than we are from the Sun. Most comets at that distance start fading as they recede, their show essentially over. 3I-ATLAS did not get the memo. Observers reported the comet remained bizarrely active after perihelion. Its coma, that fuzzy atmosphere of gas and dust, kept changing shape. Jets of material continued spraying outward. The morphology shifted in ways that defied standard comet behavior. Some astronomers quietly started calling it anomalous. Others used stronger words in private. Then the Sun joined the conversation. Around the same period, right as 3I-ATLAS was making its closest approach and staying strangely active, our star developed a monster. A sunspot region so massive it could swallow 15 Earths side by side formed on the Sun's face. And because the universe apparently enjoys dramatic irony, this colossal active region was pointing directly at us. Solar flares erupted, X-ray emissions spiked, space weather agencies recorded increases in solar flux that some reports suggest jumped by a factor of 10 over baseline levels within a week. The sun was having a meltdown and Earth was in the splash zone, so let's line up the dominoes. An interstellar visitor with a hyperbolic orbit, proven to come from outside our solar system, passes the sun and refuses to behave like a normal comet. The sun erupts with unusual violence at precisely that moment. 3 weeks later, Earth's crust starts fracturing and exploding across multiple continents simultaneously. Volcanoes that predated human civilization wake up screaming. You could call it coincidence. You could say comets pass through all the time. The sun has cycles, volcanoes erupt, earthquakes happen, and sometimes timing overlaps. That's what Occam's razor would suggest, right? The simplest explanation is usually correct. Except Occam's razor assumes we understand all the players in the game. What if there's a connection we haven't considered because our textbooks never taught us to look for it? What if the solar system isn't just a clockwork of gravity and inertia, but also a circuit of electricity and charge? What if an interstellar object passing through can flip switches we didn't know existed? The mainstream scientific community isn't talking about this yet. Not publicly. Volcanologists will tell you Halley-Gubby was probably building pressure for decades, that monitoring was insufficient, that the eruption was overdue by geological standards even if it surprised us. Solar physicists will point to the sunspot cycle, to magnetic field dynamics, to internal solar processes that need no external trigger. Seismologists will cite tectonic stress accumulation, mantle convection, the usual suspects. All of those explanations work independently. They're not wrong. But they don't explain the timing. They don't explain why a comet from interstellar space would develop a jet pointing toward the sun instead of away from it. They don't explain why the sun would throw its worst tantrum in years right as that object passes through. And they definitely don't explain why Earth would respond with a globally coordinated geological spasm within 3 weeks. Something else is happening here. Something that requires us to think bigger, weirder, and maybe a little uncomfortably about how connected everything really is. The universe might not be the cold, indifferent machine we imagine. It might be reactive, electrical, alive in ways we've been trained not to see. So here's the question that should keep you awake tonight. If an object from beyond our solar system can somehow reach across 200 million kilometers of space and shake our planet to its core, what happens when it gets even closer? Part 2. The jet that shouldn't exist. Comets are supposed to be simple. Dirty snowballs, we used to call them, back when we thought we understood these things. A lump of ice, rock, and frozen gases orbiting the sun. As they get closer to our star, heat sublimates the ice into gas. Solar radiation pressure and the solar wind push that gas and dust outward, away from the sun, forming the classic comet tail we all learned about in school. It's elegant physics. It works. We've observed it thousands of times. 3I-ATLAS looked at that rulebook and decided to improvise. When astronomers first started tracking this object seriously in July and August of 2025, they noticed something wrong. Yes, there was the expected coma, that fuzzy cloud of gas and dust surrounding the nucleus. Yes, there were signs of typical cometary activity. But there was also something else. A jet or plume of material that appeared to be pointing toward the sun, not away from it. A sunward-facing fan of dust and gas that made absolutely no sense under classical comet physics. Imagine you're standing in a windstorm. Everything loose gets blown away from you, right? Your hair streams backward, leaves fly past, dust blows away. Now imagine something flying toward you through that same wind, defying the gale. That's what 3I-ATLAS appeared to be doing. Material streaming sunward while the solar wind screams outward at 1,000,000 kilometers per hour. The James Webb Space Telescope turned its gaze on 3I-ATLAS and found more strangeness. The comet's coma was dominated by carbon dioxide, which isn't unusual for comets, but the mix of volatiles was off. Water vapour, carbon monoxide, and dust in proportions that didn't quite match what we expect from solar system comets. It was like examining someone's breath and finding familiar molecules, but in an alien ratio that makes you wonder what atmosphere they've been breathing. Then came the dust grain analysis. Researchers studying 3I-ATLAS before perihelion noticed the dust particles being ejected were unusually large, with an effective radius around 0, 0.1 millimeters, That might sound tiny, but in comet terms it's gigantic. Normal comets spray out microscopic dust. These were practically boulders by comparison. Even stranger, they were being ejected slowly, around 5 meters per second. That's slower than a professional fastball. Because of this lazy ejection speed and large grain size, the typical anti-solar tail we expect from comets only emerged late in 3I-ATLAS's approach. Early on, that weird sunward fan dominated the show. The polarization data was the final nail in the coffin of normalcy. When light bounces off dust grains, it becomes polarized, and the degree and direction of that polarization tells us about the grain size and composition. 3I-ATLAS showed what researchers called a deep and narrow negative polarization branch. This signature is essentially unheard of among comets and asteroids. It's a fingerprint that doesn't match any species in our database. So we have a comet with the wrong dust, the wrong ejection speed, the wrong tail geometry, and the wrong polarization signature. At what point do we stop calling it a comet and start calling it something else? Things get speculative here, but stay with me because the speculation is based on actual physics. What if that sunward jet isn't sublimation at all? What if it's a plasma discharge? In this model, 3I-ATLAS isn't passively outgassing like a melting ice cube. Instead, it's electrically interacting with the sun and solar wind like a conductor touching a live wire. The jets we're seeing aren't vapour, they're ionised plasma being accelerated by electromagnetic forces. The object is plugged into the solar circuit, and current is flowing. This idea lives on the fringe of astrophysics, but it's not pseudoscience. Plasma makes up 99% of the visible universe. It responds to electric and magnetic fields far more dramatically than neutral gas. If 3I-ATLAS carries an electric charge, or if its nucleus contains conductive materials, it could interact with the sun's magnetic field and the streaming solar wind in ways that mimic but fundamentally differ from sublimation. The sunward jet could be plasma following magnetic field lines back toward the sun, defying the mechanical pressure of radiation and wind through electromagnetic forces. Why does this matter? Because if 3I-ATLAS is discharging electrically, it's not just a passive visitor. It's an active participant in the solar system's electromagnetic environment. It's adding current to circuits we barely understand. And when you dump unexpected current into any system, things can destabilize. Fuses blow, breakers trip, sparks fly. The classical explanation for all this weirdness is elaborate but possible. Maybe the dust composition is unusual because 3I-ATLAS formed in a different part of some distant stellar nebula with different chemistry. Maybe the large, slow dust grains are the result of a fragile nucleus crumbling in specific ways. Maybe the polarization anomaly comes from grain shapes we haven't modelled correctly. Maybe the sunward jet is an optical illusion, or a transient effect we misinterpreted. Maybe. But how many maybes do you stack before the tower falls over? How many anomalies does it take before unusual but explainable becomes fundamentally different? Comets have been visiting the inner solar system for billions of years. We've studied hundreds of them. We've sent spacecraft to rendezvous with them, landed probes on their surfaces, analysed their composition in exquisite detail. We know comets. Except now we have an object that came from interstellar space, where the rules might be different, where chemistry and physics operated under alien conditions for millions of years, and it's showing us behaviours we've never seen before. If 3I-ATLAS is electrically active, if it's interacting with the sun not just through gravity and sublimation but through charge and current, then its passage through our solar system isn't a flyby. It's an intervention, a disturbance, a note played in a symphony we didn't know was performing. And if that's true, then the solar outburst that followed its perihelion wasn't coincidence. It was cause and effect. The sun didn't just happen to have a tantrum the same week an anomalous interstellar object passed through. The object made it happen. 3I-ATLAS reached out across millions of kilometers of space, touched the sun electrically, and the sun screamed in response. Now, here's the truly unsettling part. If an interstellar visitor can reach the sun that way, what else can it reach? Part 3. When the sun fights back. The sun is not calm. We like to think of it as steady, reliable, a constant ball of fusion that rises and sets with comforting predictability. But that's only because we're watching from a safe distance with naked eyes that can't see what's really happening. Up close, the sun is a roiling monster of plasma, magnetic fields, and violence. It boils, it erupts, it throws tantrums that could sterilize planets. And in late October 2025, Right as 3I-ATLAS made its closest approach, the Sun decided to remind us exactly what it's capable of. The trouble started with a sunspot. Sunspots are cooler regions on the solar surface, dark patches that appear when intense magnetic fields punch through from below and suppress the normal convection of plasma. They're not actually cool, they're still around 4,000 degrees Celsius, but compared to the surrounding 6,000 degree surface, they look black. Sunspots come and go with the 11-year solar cycle. We track them, we predict them, we mostly understand them. What appeared in late October was not a normal sunspot. This was a complex active region so enormous it could swallow 15 Earths laid side by side. Imagine a wound on the Sun's face large enough to fit 15 entire planets across its width. The magnetic field lines twisted and tangled like angry snakes. Energy built up in those contorted fields the way tension builds in a coiled spring, and when those fields snapped and reconnected, which they inevitably do, the energy release was staggering. Solar flares erupted from this region with alarming frequency. These aren't little sparks. A single major solar flare can release energy equivalent to millions of 100-megaton nuclear bombs exploding simultaneously. X-ray emissions spiked. Ultraviolet radiation flooded outward. The Sun's output across the electromagnetic spectrum jumped dramatically. Some monitoring stations reported increases in solar flux by factors approaching 10 times normal background levels within a single week. The Sun was having what astronomers politely call an active period. Others might call it a meltdown. The timing is what should make your skin crawl. This massive sunspot complex didn't just form randomly. It developed and became violently active during the exact window when 3I-ATLAS was making its closest pass by the Sun. The interstellar visitor reached perihelion on October 29th to 30th. The solar outburst peaked around that same period. Coincidence is one explanation. Causation is another. Standard solar physics tells us sunspots form from internal magnetic dynamo processes deep in the Sun's convective zone. The Sun rotates, plasma flows, magnetic fields get twisted and amplified. Eventually those fields rise to the surface and create active regions. It's all internal. Nothing from outside should be able to trigger this process. The Sun does its own thing on its own schedule, governed by physics that plays out over decades and centuries. Except we know magnetic fields don't stay neatly contained. They reach outward. They interact. The Sun's magnetic field extends billions of kilometers into space, forming the heliosphere that surrounds our entire solar system. That field is dynamic, constantly shifting as the solar wind carries plasma outward. When an electrically active object moves through that field, when something with its own charge or magnetic properties passes through, the system responds. Think of the Sun as a massive electrical generator and the solar system as the circuit it powers. Most objects in that circuit are passive, they absorb what comes their way and nothing more. But what if 3I-ATLAS isn't passive? What if it's conductive, charged, electromagnetically active in ways we don't normally see, because most comets come from our own solar system and have been electrically neutralized over billions of years? An interstellar visitor hasn't been part of our circuit. It spent millions of years in interstellar space under completely different conditions. It might carry charge, it might interact with magnetic fields differently. When 3I-ATLAS plunged toward the Sun, it entered the most intense part of the heliosphere. The solar magnetic field here is strong, twisted, complex. If the comet is electrically active, as that bizarre sunward jet suggests, then it didn't just pass through this environment quietly. It interacted with it. It coupled to the Sun's magnetic field. Current flowed. And when you couple new current sources into a complex electromagnetic system, the system destabilizes. The sunspot complex could be a symptom of that destabilization. Magnetic field lines that were already stressed got an extra twist from the comet's passage. Energy that was building gradually got a sudden boost. The Sun's internal dynamo, which operates on slow cycles, got kicked by an external pulse. The flare activity we observed wasn't just the Sun doing its normal thing. It was the Sun responding to a perturbation, a disturbance in the circuit that propagated inward and triggered a cascade of magnetic reconnection events. This is where mainstream science taps the brakes. Solar physicists will point out that the Sun has plenty of internal energy and complexity to explain any flare activity without invoking external triggers. They're right. The Sun doesn't need help to be violent. But that doesn't mean external factors can't influence timing or intensity. Weather systems on Earth are driven by internal atmospheric physics, but external factors like solar radiation and cosmic rays can still trigger specific storms at specific times. The same logic could apply to solar weather. The X-ray and ultraviolet radiation from those solar flares didn't just light up our instruments. They slammed into Earth's magnetosphere and upper atmosphere. Satellites experienced interference, radio communications disrupted. The ionosphere, that electrically charged layer of our atmosphere between 80 and 600 kilometers up, got pummeled with high-energy particles. Currents induced in Earth's magnetic field surged. The entire electromagnetic environment around our planet was disturbed, and here's where things get uncomfortable. Earth isn't just a passive rock floating in space. It's electrically connected to the sun through the solar wind, through magnetic field lines, through a complex web of plasma interactions we're only beginning to understand. When the sun erupts, Earth responds. We see that response in auroras, in magnetic storms, in disruptions to technology. But what if the response goes deeper? What if electromagnetic disturbances at the surface can propagate downward into the planet itself? What if the crust, the mantle, the deep interior of Earth are sensitive to electromagnetic changes in ways our textbooks don't acknowledge? The sun threw a tantrum, and 3 weeks later, Earth started shaking. That's the timeline. That's the sequence. Solar outburst followed by global volcanic and seismic activity across unconnected geological zones. The standard explanation says these are independent events. The alternative explanation says they're linked by electricity, by electromagnetic coupling between the sun and Earth's interior. One explanation requires a lot of unlikely coincidences. The other requires us to rethink how planets work. Neither option is comfortable, but one of them has to be true. So which makes you more uneasy? A universe ruled by impossible coincidence, or a universe where electricity reaches deeper than we ever imagined? Part 4. The reverse piezoelectric effect. You probably have quartz in your watch. The reason your watch keeps accurate time is because quartz crystals do something remarkable. When you apply mechanical stress to them, squeeze them or bend them, they generate an electric voltage. This is called the piezoelectric effect, discovered in 1880 by Pierre and Jacques Curie. It's fundamental to modern technology. Microphones, speakers, sonar, ultrasound imaging, cigarette lighters all rely on piezoelectricity. You press a button, stress a crystal, get an electrical spark. But here's the kicker. The effect works in reverse. If you apply an electric field to a piezoelectric crystal, it deforms. Voltage in, mechanical strain out. This is the reverse piezoelectric effect, and it's just as real and measurable as the forward version. You can make crystals vibrate, expand, contract, all by hitting them with the right electrical signal. Your phone's speaker uses this. Apply a changing voltage to a piezoelectric element, and it vibrates, creating sound waves. It's elegant, it's well understood, and nobody disputes it. Now scale it up. Earth's crust and mantle aren't made of pure quartz, but they contain enormous amounts of quartz and other piezoelectric minerals. Granite, one of the most common crustal rocks, is roughly 30% quartz by volume. The mantle contains olivine, which has piezoelectric properties under certain conditions. We're talking about quadrillions of tons of piezoelectric material extending from the surface down hundreds of kilometers. That's a lot of crystal. The question nobody wants to ask out loud is this. If you hit Earth's crust with a massive electromagnetic pulse from space, with the kind of voltage surge you'd get from a major solar storm, could you trigger the reverse piezoelectric effect on a planetary scale? Could you make the ground vibrate, flex, strain under electrical stress? Could you, in effect, squeeze magma chambers and tectonic plates with electricity? The theory sounds insane until you look at the physics. Electromagnetic fields penetrate rock. They don't stop at the surface. Ground-penetrating radar works because radio waves pass through soil and stone. Lightning strikes can induce currents in the ground that travel for kilometers. The Earth itself generates electrical currents through geodynamo processes in the core, and those currents flow through the mantle and crust. Rock is not a perfect insulator. It's conductive enough, especially when hot and under pressure, to carry current. When a major solar storm hits Earth, the electromagnetic disturbance doesn't just affect our atmosphere and magnetosphere. It induces currents in the ground, what power grid operators call geomagnetically induced currents. These can flow through pipelines, power lines, any conductive infrastructure. During the March 1989 geomagnetic storm, induced currents knocked out the entire Hydro-Quebec power grid in Canada, leaving 6 million people without electricity for 9 hours. That storm dumped enough electromagnetic energy into Earth's crust to alter the conductivity and flow patterns of underground currents over an entire continent. If induced currents can trip power grids, can they also stress piezoelectric minerals in the crust? The answer is almost certainly yes. The question is whether the effect is strong enough to matter geologically. A few millivolts across a quartz crystal in your watch makes it vibrate at a very specific frequency. A few kilovolts across kilometers of quartz-rich granite makes it do what? Flex microscopically? Probably. Enough to trigger earthquakes? That's the billion-dollar question. Earthquakes happen when stress in the crust exceeds the strength of rock. Tectonic forces build that stress over years or centuries. The crust bends, strains, stores elastic energy like a spring being compressed. Eventually something gives. The rock fractures, the fault slips, the stored energy releases as seismic waves. That's the standard model, and it's fundamentally correct. But it requires a trigger. Something has to push the system over the edge from stable stress to sudden failure. Most earthquakes self-trigger. The stress just keeps building until the rock can't hold anymore. But some earthquakes can be triggered by external factors. We know this for certain. Reservoir-induced seismicity happens when you fill a large dam reservoir and the added water weight stresses nearby faults enough to trigger quakes. Injection-induced seismicity occurs when you pump fluids underground for fracking or waste disposal, changing pore pressures and lubricating faults. Tidal forces from the moon can trigger earthquakes by adding tiny stress changes that tip already loaded faults into failure. The triggers are small, but they're real. Could an electromagnetic pulse trigger earthquakes through the reverse piezoelectric effect? If a fault is already loaded, already close to failure, and you suddenly apply a voltage across millions of tons of quartz-rich rock, could the resulting mechanical strain be enough to push it over the edge? The numbers are unclear because nobody has done this experiment at crustal scales. We don't have planetary stress labs, but the physics is sound. Apply voltage to piezoelectric material, get mechanical deformation. Scale it up, apply massive voltage across massive volumes of crustal rock, and you should get massive deformation. Whether that's enough to trigger earthquakes depends on how close the system is to failure already. Now add volcanoes to the picture. Magma chambers sit a few kilometers below volcanic mountains, pools of molten rock under tremendous pressure. They're stable until they're not. Eruptions happen when pressure exceeds the strength of the overlying rock, or when new magma injections pressurize the chamber past its breaking point, or when gases exsolve and expand. Again, there's a threshold, a tipping point. Most volcanoes cross that threshold through internal processes, but external triggers can matter. The Halley-Gubby eruption is the smoking gun here. 12,000 years dormant. No recorded historical activity, no warning signs that we detected. Then it explodes with enough violence to send ash across an entire sea. What changed? Maybe pressure had been building undetected for centuries and we just didn't notice. Maybe deep magma injections occurred in the weeks before the eruption that our sparse monitoring didn't catch. Or maybe something squeezed that magma chamber from the outside, applied a stress pulse that tipped the balance. If the crust around Halley-Gubby contains piezoelectric minerals, and if a major electromagnetic pulse from the solar storm hit that region with sufficient intensity, the reverse piezoelectric effect could have generated mechanical stresses throughout the overlying rock. Those stresses would propagate downward, compressing the magma chamber, raising the internal pressure just enough to trigger fracturing and eruption. The effect wouldn't need to be huge. Volcanic systems are already poised on the edge. A tiny push can cascade into catastrophe. The timing supports this. Solar storm peaks in late October. 3 weeks later, late November, Earth starts shaking. 3 weeks is interesting because that's roughly how long it takes for electromagnetic disturbances to propagate through complex geological systems and for mechanical stresses to accumulate to critical levels. It's not instant. Rock doesn't respond to electrical signals at the speed of light. It responds at the speed of seismic waves, the speed of stress propagation through solid material. That takes time. 3 weeks is right in the window. The global distribution supports it too. The volcanic and seismic activity in late November wasn't clustered in one region. It was worldwide, across multiple continents, multiple tectonic settings, all within a narrow time window. That's very hard to explain through normal geological processes, which are inherently local. Tectonic plates move independently. Magma chambers evolve independently. There's no mechanism in standard geology that should cause simultaneous eruptions across unconnected volcanic systems. But electromagnetic fields are global. A major solar storm hits the entire daylit side of Earth at once. If that storm triggers the reverse piezoelectric effect, it triggers it everywhere simultaneously. The response would be global, exactly like what we observed. The establishment will call this fringe science, and maybe it is, but fringe science becomes mainstream when the evidence piles up high enough to force a reckoning. We have an interstellar object behaving anomalously. We have a massive solar outburst during its passage. We have a globally synchronized geological response 3 weeks later. And we have a known physical mechanism, the reverse piezoelectric effect, that could link these events together. How much evidence do we need before we start taking this seriously? How many volcanoes have to wake up before we admit the planet might be listening to the sky? Part 5. The circuit we live inside. We were taught that space is empty, a vacuum. Planets orbit in silence, governed only by gravity's invisible hand. The sun warms us through radiation across a void. Everything is mechanical, predictable, isolated. This is the Newtonian universe, refined by Einstein, enshrined in textbooks. It works. It predicts planetary motions with exquisite precision, but it's not complete. The universe is not empty. It's full of plasma. Ionized gas, where electrons have been stripped from atoms, creating a sea of charged particles. Plasma responds to electric and magnetic fields in ways neutral gas never could. It conducts electricity. It generates magnetic fields. It forms structures, filaments, sheets, currents stretching across light years. 99% of the visible matter in the universe exists in this state. Yet we learned physics as if gravity alone ruled the cosmos. The solar system is not a gravitational clockwork floating in a void. It's an electrical circuit. The sun is the central generator, fusing hydrogen into helium and pumping out not just light and heat, but also a continuous stream of charged particles called the solar wind. This wind races outward at 400 to 800 kilometers per second, carrying magnetic field lines with it, filling the solar system with a tenuous but electrically active plasma. Planets orbit through this wind like boats on a river, not in empty space but in an ocean of moving charged particles. Earth is not electrically isolated. Our magnetosphere, generated by the spinning molten iron in our core, extends tens of thousands of kilometers into space. It's shaped like a teardrop, compressed on the sunward side by the solar wind, stretched into a long tail on the night side. This magnetosphere channels charged particles, creates currents, generates field-aligned currents that connect the ionosphere to the magnetotail. Millions of amperes flow through these circuits. We can measure them with satellites. They're real, physical, electrical currents linking the ground to space. The ionosphere, that layer of partially ionized atmosphere between 80 and 600 kilometers up, is conductive. Radio waves bounce off it. Electric currents flow through it, driven by solar radiation, by the interaction with the magnetosphere, by atmospheric winds dragging charged particles. Below the ionosphere is the neutral atmosphere, and below that is the ground. But the electrical connection doesn't stop. Lightning proves that. Every thunderstorm is a breakdown of electrical insulation between the ground and the ionosphere, a discharge channel allowing charge to flow vertically through the atmosphere. Earth's surface maintains an electric potential relative to the ionosphere of a few 100,000 volts. We live on one plate of a giant spherical capacitor. The ground itself is conductive, more so when wet, less when dry, but never perfectly insulating. Minerals in rock, especially when compressed and heated at depth, conduct electricity. The mantle, though solid on human timescales, is warm enough that some charge carriers can move. The outer core is liquid iron nickel, a nearly perfect conductor where convection and rotation generate Earth's magnetic field through dynamo action. That process is electrical at its core, pun intended, so we have circuits upon circuits. The sun generates electromagnetic energy and sprays it outward. Earth intercepts that energy with its magnetosphere, funnels it through field-aligned currents into the ionosphere. From there it couples to the ground through atmospheric conductivity and occasional lightning strikes. Currents flow through the crust, into the mantle, connect to the geodynamo in the core. It's all linked. The whole system, from the solar surface to Earth's centre, is one enormous, complex dynamic electrical circuit. Most of the time this circuit hums along at a steady state. The Sun varies slightly with its 11-year sunspot cycle, but even at solar maximum the variations are relatively mild. Earth's internal processes, the geodynamo and tectonic activity, operate on their own timescales, mostly independent of solar variations. The coupling between solar weather and geological activity is weak under normal conditions, weak but not zero. We know geomagnetic storms affect the ionosphere and can induce currents in pipelines and power grids. We know solar energetic particle events can alter atmospheric chemistry. The connections are there, just usually subtle. 3I-ATLAS changed the equation. An interstellar object with anomalous electrical properties, as suggested by that sunward jet, entered the solar system and passed close to the Sun. It coupled to the solar magnetic field, disturbing the local electromagnetic environment. The Sun responded with a massive eruption, a sunspot complex and associated flares that pumped far more energy into the heliosphere than normal. That energy, in the form of X-rays, ultraviolet radiation, and enhanced solar wind, slammed into Earth. Our magnetosphere, already a conduit for current, got hit with a surge. Think of it like turning up the voltage on a power supply. If the circuit is stable, it just runs hotter, more current flows, but nothing breaks. If the circuit is already stressed, if components are near their failure limits, a voltage surge can cause cascading failures. Fuses blow, capacitors rupture, transistors fry. Earth's geological system, the tectonic plates and magma chambers, might be like stressed circuit components. Most of the time they're stable, but if you hit them with an electromagnetic surge through the reverse piezoelectric effect, if you suddenly apply unusual mechanical stresses through electrical means, you can trigger failures. Earthquakes, eruptions, exactly what we observed. The circuit model explains the timeline. Solar event in late October. Electromagnetic surge propagates through Earth's magnetosphere, ionosphere, and into the crust. Stress builds in piezoelectric minerals over days to weeks. Critical thresholds are crossed. Failures begin in late November. The delay makes sense. Electrical signals propagate fast, but mechanical responses in rock are slow. Stress diffusion, crack propagation, magma pressurization, these are rate-limited processes. 3 weeks is a reasonable timescale for electromagnetic perturbations to translate into geological action. The circuit model also explains the global distribution. If the trigger is electromagnetic, originating from the Sun and coupling through Earth's magnetosphere, then it affects the entire planet simultaneously. Different regions will respond differently based on local geological conditions. A volcano already near eruption will go first. A fault already loaded will slip sooner. But the trigger is global, so the response is widespread and synchronized. You don't get that with normal tectonic processes, which are inherently local and independent. You only get synchronized global geological activity if there's a common external driver. The circuit provides that driver. We've been blind to this because our disciplines are siloed. Geologists study the solid Earth. Atmospheric scientists study the air. Solar physicists study the Sun. Each group uses different tools, different equations, different assumptions. The idea that solar events could directly affect geology seems absurd when you're trained to think of rock and space as separate realms. But they're not separate. They're connected by electromagnetism, by currents and fields that flow through the entire system. Once you see the circuit, once you recognize that Earth is not isolated but embedded in a vast electrical network powered by the Sun and influenced by anything that disturbs that network, the connections become obvious. 3I-ATLAS disturbed the network. It entered the circuit and flipped switches we didn't know existed. The Sun noticed. Earth noticed. And now we're watching the consequences unfold in real time as volcanoes wake and the ground shakes. The question isn't whether the circuit exists, it's whether we're ready to understand what it means. Because if a comet can do this from 200 million kilometers away, just by passing close to the Sun, what happens when it comes closer to us? Part 6. The approach vector. 3I-ATLAS is not done with us. Perihelion, its closest approach to the Sun, happened in late October. That was round 1. Now the comet is on an outbound trajectory, moving away from the Sun but not away from Earth. Orbital mechanics is funny that way. Depending on the angle and timing, an object leaving the inner solar system can still pass close to a planet on its way out. 3I-ATLAS is on exactly that kind of path. The comet is heading our way. Current trajectory calculations, based on observations through early November, suggest 3I-ATLAS will make its closest approach to Earth in late December 2025. Closest approach doesn't mean impact. Don't panic yet. It means the point where the comet's orbit brings it nearest to our planet, the minimum distance it will reach before continuing on its hyperbolic path out of the solar system forever. That distance will still be measured in millions of kilometers. Space is big. Close in astronomical terms is still unfathomably far by human standards. But close enough matters when you're talking about electromagnetic effects. Gravity falls off with the square of distance. Electromagnetic forces can fall off even faster depending on the configuration, but they can also propagate through conducting media in complex ways that don't follow simple, inverse, square laws. Plasma is weird. Magnetic field lines can carry currents across vast distances. The solar wind connects the Sun to the outer edge of the heliosphere, billions of kilometers away, through a web of magnetic fields and flowing charged particles. If 3I-ATLAS is electrically active, its sphere of influence might be larger than its gravitational sphere. 3 weeks ago, the comet was at 1.4 astronomical units, about 210 million kilometers from the Sun, and even farther from us. At that distance, it still managed to disturb the Sun enough to trigger a massive solar outburst, assuming the circuit model is correct. Now it's getting closer to Earth. Not a straight shot. Orbital mechanics doesn't work that way, but closer in terms of minimum separation. By late December, estimates put the closest approach somewhere between 0.4 and 0.6 astronomical units from Earth. That's 60 to 90 million kilometers, roughly half the distance between Earth and the Sun, close by solar system standards. If the comet could influence the Sun from 200 million kilometers, what can it do from 90 million? Distance matters, but so does geometry. When 3I-ATLAS passed the Sun, it was moving through the most intense part of the heliosphere, where the solar magnetic field is strongest and the Sun's influence dominates. As it moves outward, it's entering a different electromagnetic environment. The solar wind is slower, more diffuse, but Earth's magnetosphere is a significant magnetic structure in its own right. The comet will be passing through Earth's magnetotail, or very close to it, depending on exact timing and geometry. That's a direct electromagnetic connection. Earth's magnetotail is the elongated extension of our magnetosphere on the night side, stretched out by the solar wind like smoke from a chimney in a breeze. It extends beyond the Moon's orbit, reaching hundreds of thousands of kilometers downstream from Earth. The tail contains 2 lobes of magnetic field lines pointing in opposite directions, separated by a current sheet where particles are trapped and energized. This is where geomagnetic substorms occur, where energy from the solar wind is stored and suddenly released, causing auroras and magnetic disturbances on the ground. The magnetotail is not a passive structure. It's electrically active, full of currents, plasma, and dynamic field reconfigurations. If 3I-ATLAS passes through or near the magnetotail, it could interact with that structure directly. An electrically charged or magnetically active comet in that environment would be like dropping a wire into a transformer coil. Currents would be induced, magnetic field lines would reconnect, energy would flow between the comet and Earth's magnetic system. The coupling could be even stronger than what happened with the Sun, because the magnetotail is specifically structured to channel energy back toward Earth. Solar wind energy captured in the tail eventually gets dumped into the ionosphere and down to the ground. If the comet adds energy to that system, if it perturbs the tail dynamics, we could see geomagnetic storms far more intense than what solar flares alone would produce. Geomagnetic storms are classified on a G scale from 1 to 5, with 5 being the most severe. A G5 storm, which happens maybe once per solar cycle, can cause widespread voltage control problems in power grids, damage transformers, disrupt satellite operations, create aurora visible at low latitudes, and induce powerful currents in pipelines and communication cables. The 1989 Quebec blackout was a G5 event. The 1859 Carrington event the most powerful geomagnetic storm in recorded history, would have been off the scale. Telegraph systems sparked and caught fire. Auroras were visible in the tropics. If that happened today, the damage to modern infrastructure would be catastrophic. Now, imagine a G5-level storm, but sustained for days or weeks instead of hours. Imagine the induced currents not just disrupting power grids, but stressing the crust through piezoelectric effects continuously. Imagine volcanoes around the world, already triggered once by the perihelion event, getting hit with another electromagnetic pulse, stronger and longer duration, as the comet makes close approach to Earth. What happens to a magma chamber that gets squeezed twice in 2 months? What happens to faults that slipped once and are reloading under tectonic stress when another electrical trigger hits before they've fully stabilized? The worst-case scenario is a cascade. First eruption weakens the crust around a volcanic system. Gas pressure in the magma chamber adjusts. The system is now more sensitive to perturbations, closer to a critical state. Second electromagnetic pulse hits during close approach. Reverse piezoelectric effect generates another stress wave. The already weakened system fails catastrophically. Eruptions that might have taken decades to build up happen in weeks. Faults that slipped slightly in November slip further in December. Earthquakes trigger aftershocks, trigger more earthquakes. Geological instability feeds back on itself, amplified by repeated electromagnetic kicks from the passing comet. Indonesia is particularly vulnerable. The country sits on the Pacific Ring of Fire, the most volcanically and seismically active region on Earth. Over 100 active volcanoes, multiple subduction zones where oceanic plates dive beneath continental crust, generating magma and stress. The region already showed unusual activity in late November. If another trigger hits in late December, if multiple Indonesian volcanoes erupt simultaneously, or in rapid succession, the humanitarian consequences would be devastating. Millions of people live near active volcanic systems. Ashfall can disrupt agriculture, contaminate water, collapse roofs. Pyroclastic flows can obliterate towns in minutes. Tsunamis generated by submarine eruptions can strike coasts with no warning. This isn't speculation, it's history. Krakatoa in 1883, Tambora in 1815, these eruptions killed tens of thousands and altered global climate for years. Kamchatka, Alaska, the Aleutian Arc, Central America, the Andes, all part of the Ring of Fire, all active, all vulnerable. If the circuit model is correct, if electromagnetic triggers can induce geological failures globally, then a close pass by an electrically active comet could light up the entire Ring of Fire like a string of firecrackers. We're not talking about one volcano. We're talking about dozens, maybe more, entering eruptive phases within days or weeks of each other. The ash injection into the atmosphere alone would be enough to affect weather patterns, disrupt air travel, possibly cool global temperatures if the sulfur output is high enough. Then there's the possibility we haven't discussed yet. What if 3I-ATLAS doesn't just trigger existing geological systems? What if it can affect Earth's magnetic field directly? The geodynamo in our core is electromagnetic. It's generated by convection and rotation in the liquid outer core, but it's sustained by electrical currents flowing through molten iron. Those currents create Earth's magnetic field, which shields us from solar wind and cosmic radiation. The field is strong, but it's not static. It wanders, it fluctuates, and over geological time it reverses, north becoming south and vice versa. We don't fully understand what triggers reversals. They seem random, happening every few 100,000 years on average, but the last one was 780,000 years ago. We're overdue. Could a major electromagnetic disturbance from an external source push the geodynamo toward instability? Could it trigger a magnetic field excursion, a temporary weakening or directional shift that doesn't fully reverse but still disrupts the field for decades or centuries? We've seen excursions in the paleomagnetic record, rapid field changes that happened over just a few hundred years. The Lachamp event 39,000 years ago saw the field strength drop to less than 10% of normal before recovering. During that time, Earth's radiation shielding was compromised. Cosmic rays penetrated deeper into the atmosphere. The effects on life and climate are debated but probably significant. If 3I-ATLAS can induce currents in Earth's crust strong enough to trigger earthquakes and eruptions, could those currents propagate deeper into the mantle, possibly even affecting the flow patterns in the outer core? The idea sounds absurd until you remember that the entire planet is electrically connected. Currents induced at the surface can flow downward if there's a conductive path. The mantle is hot and under pressure. At depths below a few hundred kilometers, the conductivity increases. Currents can flow. If massive electromagnetic pulses from the comet's close approach dump enough energy into the crust and mantle, some of that energy could couple to the geodynamo. It might not be enough to trigger a full reversal. Those probably require much larger energy inputs sustained over millennia. But an excursion, a temporary field weakening, that's within the realm of physical possibility. The consequences of a magnetic field excursion in the modern era would be catastrophic. Our technology depends on stable magnetic fields. GPS navigation uses precise magnetic field models. Communication satellites operate in orbits designed for current radiation belt configurations. Power grids are shielded based on expected geomagnetic storm intensities. If the field weakens or shifts rapidly, all of those assumptions break. Radiation exposure for astronauts and airline crews increases. Satellite electronics degrade faster. Auroral zones shift, bringing geomagnetic storms to latitudes that have never experienced them before. And we wouldn't see it coming because we've never seen a magnetic field excursion triggered by an external object. 3I-ATLAS is approaching. We're watching, tracking, calculating its orbit with increasing precision, but we're still thinking about it as just a comet, a lump of ice and rock on a predictable Keplerian trajectory. We're measuring its position and velocity, checking whether it might hit us gravitationally. We're not measuring its electrical properties. We're not monitoring its interaction with the solar wind in real time. We're not preparing for the possibility that this object might be carrying the power to shake our planet again, harder this time, as it passes closer than it's ever been. Maybe we should start. Part 7. The Historical Whispers. This isn't the first time. That's the part nobody wants to admit. The idea that cosmic visitors could trigger geological upheaval isn't new speculation invented to explain 3I-ATLAS. It's been whispered about in the margins of science for decades, dismissed as fringe thinking, but never entirely debunked because the historical record keeps whispering back. Halley's Comet, the most famous comet in history, returns every 75 to 76 years. We've got solid records of its passages going back over 2,000 years. Chinese astronomers tracked it meticulously. European records are less consistent but still useful. What's interesting is when you line up major Halley's Comet passages with geological and climate events. The correlation isn't perfect, but it's there often enough to make you wonder. Take the passage of 1198 CE. Halley appeared in the sky that September. Within months, Europe experienced unusual seismic activity. The Levant saw significant earthquakes. Volcanic activity increased in Iceland. Could be coincidence. History is full of earthquakes and eruptions, but 1198 wasn't an isolated case. The 530 AD passage coincided with significant environmental disruption across the Eastern Roman Empire. The late 530s and 540s saw what historians call the Late Antique Little Ice Age, a period of cooling possibly triggered by massive volcanic eruptions. Ice core records show sulfur spikes suggesting major eruptions around that time. Tree ring data shows stunted growth indicating cold conditions. Byzantine sources describe famines and a dimmed sun. Halley's Comet passed through right before this mess started. Go further back. The comet passage in 66 AD was famously recorded by Roman historians as an omen presaging disaster. That same year, Vesuvius showed signs of unrest. Earthquakes rattled the Bay of Naples. 12 years later, in 79 AD, Vesuvius erupted catastrophically, destroying Pompeii and Herculaneum. Did the comet trigger a slow destabilization? Was the earthquake activity in 66 part of a process that culminated in the 79 eruption? Nobody knows, but the timing raises questions. Move to more recent, better documented cases. The Great Comet of 1811, visible for months, was followed by the New Madrid earthquakes of 1811 to 1812, some of the most powerful earthquakes in North American history. The Mississippi River briefly flowed backward. Temporary waterfalls formed. Church bells rang spontaneously in Boston from the seismic waves. Eyewitnesses reported strange atmospheric phenomena, lights in the sky, sounds like distant thunder on clear nights. Could be pure coincidence. The New Madrid seismic. Zone is active, earthquakes happen there. But the 1811 to 1812 sequence was exceptional in its power and duration. and it happened right after a spectacular comet display. The Tunguska event of 1908 is another data point, though not a comet passage but an impact. A small asteroid or comet fragment exploded over Siberia with the force of 10 to 15 megatons of TNT, flattening 2,000 square kilometers of forest. What's less known is that in the years following Tunguska, global volcanic activity increased noticeably. 1912 saw the Novarupta eruption in Alaska, one of the largest volcanic eruptions of the 20th century. 1919 brought the major eruption of Kelad in Indonesia. Could the Tunguska shockwave have stressed already loaded volcanic systems? Could the electromagnetic pulse from the airburst have triggered geological responses? It sounds wild, but the numbers suggest it's possible. The problem with all these historical cases is lack of precise data. We don't have electromagnetic field measurements from the Middle Ages. We don't have seismographs from the Roman Empire. We're relying on written records that may be incomplete or misinterpreted, ice core data that gives us sulfur spikes but not causes, tree rings that show cooling but not why. The correlation between comet passages and geological unrest could be real, or it could be observational bias, humans noticing connections that aren't there because comets are dramatic and memorable. But here's the kicker. We're now living in the first era where we can actually test this hypothesis with real data. We have seismographs covering the entire planet. We have satellite monitoring of volcanoes. We have magnetometers measuring Earth's magnetic field continuously. We have solar observatories watching the sun in multiple wavelengths. We have spacecraft tracking comets and measuring their composition and electromagnetic properties. For the first time in history, when an interstellar comet passes through the inner solar system, we can watch everything that happens and measure it precisely. We can see if the geological response is real or imagined. 3I-ATLAS is our experiment. The late November volcanic eruptions are data points in that experiment. Hale-Gubby, dormant for 12,000 years, erupts 3 weeks after a major solar outburst caused by, or coincident with, an anomalous comet passage. Multiple other volcanic systems show increased activity in the same time window. Earthquake clusters appear globally. If this were an isolated case, you'd dismiss it. But stacked on top of the historical whispers, stacked on top of the known physics of the reverse piezoelectric effect, stacked on top of the proven electromagnetic coupling between the Sun and Earth, it starts looking less like coincidence and more like confirmation. Scientists are conservative by training. That's good. It prevents us from jumping to conclusions based on insufficient evidence. But conservatism can also blind us to patterns that don't fit our models. For a century, geologists have insisted that Earth's interior processes are independent of cosmic influences, aside from tidal forces and the occasional asteroid impact. The idea that a passing comet could affect volcanism or seismicity has been treated as astrology, not astronomy. But what if the ancients who saw comets as omens of disaster weren't entirely superstitious? What if they were observing a real pattern that we've only now developed the tools to verify? The historical record suggests that major cometary passages, especially those involving unusual comets, or comets that come very close to Earth, are often followed by geological unrest within months to years. The mechanism wasn't understood. It was attributed to divine intervention, to celestial influence, to mystery. Now we have a potential mechanism. Electromagnetic coupling through the solar circuit, reverse piezoelectric effects in the crust, solar outbursts triggered or amplified by cometary disturbances. The pieces fit together if you're willing to look at the puzzle from a different angle. 3I-ATLAS is not just another comet. It's a proven interstellar visitor with proven anomalous behavior and proven correlation with geological unrest on Earth. If the historical pattern holds, if the mechanism is real, then what we saw in November was just the opening act. The comet is getting closer. The electromagnetic coupling should strengthen. The geological response should intensify. We're watching history repeat, but this time with instruments precise enough to see exactly how the music plays. The ancients couldn't warn us because they didn't understand what they were seeing. We have no such excuse. The data is coming in. The pattern is emerging. The question is whether we'll have the courage to accept what it's telling us before the next verse begins. Part 8. The Silence from the Establishment. You'd think a 12,000-year-old volcano exploding 3 weeks after an anomalous interstellar comet triggers a solar outburst would make headlines everywhere. You'd think scientific conferences would be buzzing with debate. You'd think NASA, ESA, the USGS, every major space and earth science agency would be issuing statements, organising task forces, demanding more observations. You'd be wrong. The silence is deafening. Go search for official statements connecting 3I-ATLAS to geological activity. You'll find nothing. The comet gets mentioned in astronomy circles as an interesting interstellar visitor worth observing. Halley-Gubby's eruption gets a few volcanology papers noting it was unexpected, but attributing it to unmonitored pressure buildup. The solar storm gets standard space weather reports warning about satellite interference and auroral displays. Each event is catalogued, analysed and filed away in separate boxes. Nobody is drawing lines between the boxes. Why not? There are several possible explanations, and not all of them are sinister. First, science moves slowly. Publishing a paper suggesting a causal connection between an interstellar comet and volcanic eruptions would require extraordinary evidence. You'd need to demonstrate the physical mechanism convincingly. You'd need statistical analysis showing the correlation is significant. You'd need to address every alternative explanation. That takes time, often years. The eruption happened in November. We're barely a month out. No peer-reviewed research connecting these events could possibly exist yet. Second, scientists are specialists. Astronomers study comets. Solar physicists study the sun. Geologists study volcanoes. Each group uses different data, attends different conferences, reads different journals. The idea that a comet could affect volcanoes crosses so many disciplinary boundaries that nobody feels qualified to make the connection publicly. An astronomer might notice the timing, but doesn't have expertise in volcanology to evaluate whether it's meaningful. A volcanologist might be aware of the solar storm but doesn't know enough plasma physics to assess electromagnetic coupling mechanisms. The connection requires someone fluent in multiple fields, and those people are rare. Third, and this is where it gets uncomfortable, there's institutional resistance to ideas that challenge fundamental paradigms. For over a century, geology has operated on the principle that Earth's interior processes are driven by internal heat and tectonic forces, period. External factors like solar activity are acknowledged for atmospheric and climate effects, but not for geological effects. The textbooks don't include sections on electromagnetic triggering of earthquakes. The models don't incorporate piezoelectric stress from geomagnetic storms. Suggesting that a comet could trigger eruptions is suggesting that the entire field has missed something fundamental. That's a hard sell. Career suicide for a junior researcher. A legacy risk for an established scientist. Fourth, there's the public panic factor. If a government agency or major scientific institution publicly suggested that an approaching comet could trigger global geological chaos, what happens? Stock markets crash. People flee coastal areas near volcanoes. Conspiracy theories explode. Social media melts down. Even if the science is solid, the societal consequences of making such an announcement are severe. Decision-makers face a nasty calculation. Warn people and risk causing a panic that might be unwarranted if the hypothesis is wrong, or stay quiet and risk being blamed for not warning people if it's right. In that situation, institutional inertia favours silence until the evidence is absolutely overwhelming. But here's the thing about silence. It doesn't mean nothing is happening. It just means nothing is being said publicly. Behind closed doors, data is being collected. Seismologists are tracking the unusual earthquake clusters. Volcanologists are watching the systems that activated in November to see if they stay active. Solar physicists are monitoring 3I-ATLAS as it continues outbound, measuring its properties more carefully now that it's proven interesting. Space weather forecasters are running models of the comet's trajectory relative to Earth's magnetosphere. The work is happening. It's just not being talked about in press releases. There are rumours, if you know where to look. Certain volcanology forums have threads questioning the timing of recent eruptions. Amateur astronomers tracking 3I-ATLAS are posting speculative threads connecting it to geological events. A few scientists have tweeted obliquely about unusual patterns without making explicit claims. Nobody wants to be first to stick their neck out, but the whispering is starting. The connections are too obvious to ignore completely. Eventually someone will publish. Someone will break the silence, either because the evidence becomes undeniable, or because the next round of geological activity, if it comes during the comet's close approach, forces the issue. The question is whether that someone will be mainstream or fringe, if established institutions continue to stay silent, if universities and government agencies refuse to investigate the connection, then the story will be picked up by alternative sources, independent researchers, bloggers, podcasters, people outside the establishment who have less to lose and more willingness to speculate. That might get the information out faster, but it also risks contaminating the legitimate scientific questions with less rigorous thinking. Once an idea gets branded as conspiracy theory, it becomes nearly impossible to rehabilitate, even if the underlying science is sound. This is how paradigm shifts happen. Not through orderly transition, where everyone agrees the old model is insufficient and logically adopts the new one. That's the fairy tale version. Real paradigm shifts are messy, political, generational. The old guard resists because their careers are built on the old paradigm. The new guard pushes because they don't have as much invested in the status quo. Evidence accumulates on both sides. Arguments get heated. Eventually, either the new paradigm proves itself through successful predictions the old model can't make, or the old guard retires and the new guard takes over by attrition. It takes decades, sometimes generations. We might be at the beginning of that process right now with the electric universe model, or at least a moderate version of it that acknowledges electromagnetic coupling plays a bigger role in solar system dynamics than currently accepted. 3I-ATLAS could be the catalyst. If the comet's close approach in late December triggers another round of geological activity, if the correlation becomes undeniable, if predictions based on the electromagnetic model prove accurate while standard models offer no explanation, then the silence will break. Scientists will be forced to engage with the idea because ignoring it will become untenable. But if nothing much happens in December, if the comet passes without obvious geological consequences, then the establishment will breathe a sigh of relief, and the whole thing will be memory hold. The November eruptions will be written off as coincidence. The solar storm will be just another solar storm. 3I-ATLAS will be just another interesting comet. The paradigm will hold, and maybe that's the correct outcome. Maybe the connection isn't real. Maybe we're seeing patterns in noise. That's possible. What's not acceptable is refusing to look. What's not acceptable is institutional silence when there are legitimate scientific questions to investigate. If the hypothesis is wrong, then study it and prove it wrong. Publish papers showing why the electromagnetic mechanism can't work at the required scales. Demonstrate statistically that the correlation between comet passages and geological activity is no better than random chance. Do the science. Don't just ignore inconvenient questions because they don't fit the model. The silence from the establishment is a choice. It's a choice to prioritize institutional stability over inquiry. It's a choice to avoid risk rather than pursue truth. And it's a choice that might come back to haunt us if 3I-ATLAS has more surprises in store. Because the comet doesn't care about our paradigms, our careers, our comfort zones. It's going to do what it's going to do. And if we're not watching, if we're not prepared, if we've silenced the warnings because they were too weird to take seriously, then we'll have no one to blame but ourselves when Earth starts shaking again. Part 9. What happens next? Late December 2025. That's when 3I-ATLAS makes its closest approach to Earth. The exact date depends on final trajectory refinements, but current estimates put it somewhere between December 20th and December 30th, holiday season. Most of the Northern Hemisphere will be on vacation, schools closed, governments running skeleton crews. Not the ideal time for a potential global geological crisis, but the universe doesn't consult our calendars. Here's what we know will happen. The comet will reach its minimum distance from Earth, somewhere between 60 and 90 million kilometers, depending on whose orbital calculations you trust. At that range, gravitational effects are negligible. 3I-ATLAS is tiny, maybe a few kilometers across at most. Its gravitational pull on Earth is less than that of a small car parked on the other side of the planet. Zero. Irrelevant. Forget gravity. This isn't about gravity. It's about where the comet passes in relation to Earth's magnetosphere. The magnetotail extends hundreds of thousands of kilometers downstream from Earth on the night side. The comet's trajectory will take it through or very near that structure. The exact geometry matters enormously. If 3I-ATLAS passes through the center of the magnetotail, through the plasma sheet where currents are strongest, the electromagnetic coupling will be maximum. If it passes to the side, the coupling will be weaker but still potentially significant. If by some chance the comet passes on the sunward side of Earth, interactions will be different, possibly less direct. We won't know the precise geometry until a few days beforehand when orbital uncertainties narrow. Comets outgas unevenly as they rotate. and as different areas of their surface get heated by the sun. Those outgassing events create tiny thrust forces that alter the trajectory slightly. It's like trying to predict exactly where a balloon will land when you release it. The path wobbles based on how the air escapes. 3I-ATLAS is doing that on a cosmic scale. Small trajectory changes of a few thousand kilometers don't matter for impact prediction, because we know it won't hit us, but they matter a lot for determining electromagnetic interactions. Assuming a magnetotail passage, here's the sequence we should expect if the electromagnetic hypothesis is correct. First, as the comet enters the outer regions of Earth's magnetosphere, space weather monitoring satellites will detect disturbances, magnetic field lines will show unusual configurations, plasma densities will shift, electric currents flowing in the magnetotail will change intensity or direction. These effects should be detectable hours to days before closest approach. If space weather agencies are paying attention, this is when the alerts should start. Geomagnetic storm warnings. Not because of solar activity, but because of direct comet interaction with Earth's magnetic environment. Next, as coupling intensifies, we should see enhanced auroral activity even if solar conditions are quiet. Auroras happen when charged particles follow magnetic field lines into the upper atmosphere and excite atoms, causing them to glow. Normally, those particles come from the solar wind, funneled down toward the poles by Earth's dipole magnetic field. But if the comet is injecting additional charged particles or disturbing magnetotail dynamics, auroras could appear at unusual latitudes, in unusual colours, with unusual patterns. Observers in the northern and southern hemispheres might see sky shows that don't match standard auroral morphology. Simultaneously, ground-based magnetometers should register anomalies. These instruments measure tiny changes in Earth's magnetic field at the surface. During geomagnetic storms, they show characteristic patterns of disturbance. If the comet is causing electromagnetic coupling, the magnetometer signatures might be different from typical solar storm patterns. Frequencies, intensities, directional changes all could deviate from the norm. Researchers monitoring this data in real time will know something unusual is happening. Then comes the critical window. If the reverse piezoelectric effect is real, if electromagnetic disturbances can stress the crust enough to trigger geological failures, then we should see increased seismic and volcanic activity starting within days of closest approach and continuing for weeks afterward. This is where prediction gets hard because we don't know which volcanic or seismic systems are closest to critical thresholds. 3I-ATLAS can't create earthquakes or eruptions where there's no existing stress or magma. It can only trigger systems that are already loaded, already near failure. The question is how many such systems exist right now around the world. The Ring of Fire is the most likely hotspot. Indonesia, Philippines, Japan, Aleutians, Alaska, Cascades, Central America, Andes. All of these regions have active subduction zones, magma chambers, stressed faults. Many showed unusual activity in November. If they get hit with another electromagnetic trigger in December, some will respond. How many? Which ones? Nobody knows. We don't have good enough monitoring of volcanic systems globally to say which magma chambers are pressurized, which faults are loaded. We're flying blind. Worst case scenario, multiple major eruptions within a short time frame. Major means VEI 4 or higher on the volcanic explosivity index, eruptions that inject significant ash into the stratosphere, affect regional climates, displace populations. If 3 or more such eruptions happen simultaneously in different locations, the compound effects would be severe. Ash clouds disrupt air travel not just regionally but globally, because flight paths have to be rerouted. Crop damage from ash fall in multiple agricultural zones could affect food supplies. Sulfur dioxide injected into the stratosphere reflects sunlight, potentially causing short-term cooling. Multiple eruptions amplify all of these effects. Then there's the possibility of a mega-eruption, something truly catastrophic. The last V7 eruption was Tambora in 1815. It killed tens of thousands directly and caused the year without a summer in 1816, leading to crop failures and famine across the northern hemisphere. A V8 eruption, a super-eruption, hasn't happened in recorded human history. Toba, 70,000 years ago, was V8 and may have brought humanity to the brink of extinction. There are a few volcanic systems on Earth capable of V8, Yellowstone, Taupo, several calderas in Indonesia. These systems operate on timescales of hundreds of thousands of years. The probability of any one of them erupting in any given year is vanishingly small. But if electromagnetic triggers can push stress systems over the edge, and if one of these supervolcano systems happens to be closer to critical than we think, then even a small push could be catastrophic. Nobody seriously thinks 3I-ATLAS will trigger a super eruption. The odds are astronomically low. But a month ago, nobody thought a 12,000-year dormant volcano in Ethiopia would explode either. The universe keeps surprising us. The systems we think are stable sometimes aren't. Earthquakes are harder to predict than eruptions because the triggering threshold is sharper. Magma chambers can show precursor signals, ground deformation, gas emissions, increased seismicity, sometimes months before eruption. Earthquakes can happen with no warning. A fault can sit stable for centuries and then slip in seconds. If electromagnetic pulses are stressing faults through piezoelectric effects, the triggering window might be very narrow, hours to days. That's not enough time to evacuate cities. It's barely enough time to send out emergency alerts. The major urban areas at risk are the same ones that always are. Tokyo, Los Angeles, San Francisco, Seattle, Mexico City, Manila, Santiago, any city near active faults or subduction zones. These cities have earthquake preparedness plans, building codes designed to withstand seismic shaking. They'll survive. But damage could be extensive if a major quake hits during the December holiday period, when emergency response might be slower due to staffing and weather. Winter earthquakes in places like Alaska or northern Japan have the added complication of cold, which complicates rescue and recovery. The timeline to watch is mid-December through mid-January. Closest approach happens late December, but if the November events are any guide, the geological response will lag by 1 to 3 weeks. Stress induced by electromagnetic pulses needs time to propagate through the crust and reach critical systems. So even if the comet passes uneventfully from a space weather perspective, we should stay vigilant into January. Absence of immediate effect doesn't mean absence of effect. What should people do? For most of the world, nothing. This isn't an evacuation-level threat. Life goes on. But if you live near an active volcano or in a major seismic zone, this might be a good time to review your emergency kit. Make sure you have water, food, flashlight, radio, the basics. Know your evacuation routes. Have a plan for where you'll go if a major quake or eruption happens. This is stuff you should be doing anyway if you live in these regions, but the late December to early January window is worth extra attention. If you're in the scientific community, pay attention to the data. Watch the seismographs. Monitor space weather. Correlate timing of any geological events with electromagnetic disturbances. Collect the evidence. This is our one chance to test the hypothesis in real time with modern instruments. If there's a connection, we'll see it. If there's not, that's important to know too. Either way, we learn something, and if nothing happens, if late December comes and goes, the comet passes, and Earth stays quiet, then either the hypothesis is wrong, or we got lucky because no critical systems were pushed over the edge this time. The absence of triggered events wouldn't disprove the mechanism. It would just mean the trigger wasn't strong enough, or the targets weren't vulnerable enough. But it would take a lot of pressure off the paradigm debate. The establishment could relax, and we could go back to treating comets as astronomical curiosities with no geological significance. Somehow, though, I don't think that's how this plays out. The universe has been nudging us all year, showing us anomalies, breaking patterns, whispering that something deeper is going on. 3I-ATLAS isn't done teaching us. Late December will be the final exam. The question is whether we'll pass or whether we'll learn the hard way that some cosmic visitors do more than just put on a pretty light show. Either way, the answer is coming, and unlike the comet, we can't look away. Part 10. The unspoken implications. Let's say it's all true. Let's say the electromagnetic hypothesis is correct. 3I-ATLAS, through some combination of charge, magnetic properties, and plasma interactions, disturbed the Sun, which erupted, which caused Earth's crust to stress through piezoelectric effects, which triggered the November geological outburst. Let's say the pattern holds in December, and we see another round of seismic and volcanic activity coinciding with the comet's close approach. Let's say the correlation becomes undeniable, published, accepted. What then? First implication is that our understanding of planetary geology is incomplete. Not wrong, but incomplete. Earthquakes and eruptions are primarily driven by internal processes, tectonic stress, mantle convection, magma generation. All of that remains true. But there's an external forcing factor we've been ignoring. Electromagnetic perturbations from space can modulate the timing and possibly the intensity of geological events that were already primed to happen. We need to rewrite textbooks, not scrap them, just add a chapter. Chapter 12, Electromagnetic Triggers for Seismicity and Volcanism. It sounds absurd until it's not. Second implication is that we've been lucky. Civilization has developed over roughly 10,000 years from the end of the last ice age to now. During that time, we've experienced plenty of volcanic eruptions and earthquakes, but nothing globally synchronized and catastrophic on the scale that electromagnetic triggers could potentially cause. We haven't seen a V8 supereruption. We haven't seen a year where a dozen major volcanoes erupt simultaneously. We haven't experienced a geomagnetic storm powerful enough to destroy modern infrastructure, coinciding with widespread geological collapse. Why not? Partly because such events are rare statistically, but also maybe because we haven't had a really bad cosmic visitor during our window of vulnerability. The big comets, the close-passing interstellar objects, the major solar outbursts, they haven't aligned in the worst possible way yet. Yet. 3I-ATLAS is not the worst possible case. It's electrically anomalous, yes, but it's not huge. It's passing at a respectful distance, millions of kilometers. It's not going to impact us. If this object, relatively small and relatively distant, can trigger volcanic eruptions on Earth, what could a larger object do? What could a comet 10 times the mass passing 10 times closer accomplish? What about an interstellar object on a direct collision course, ploughing into Earth's magnetosphere at high velocity, electromagnetically coupling with maximum intensity before physical impact even occurs? We build asteroid defense scenarios around kinetic impact, the physics of rocks hitting planets. We don't model the electromagnetic precursor effects. Maybe we should. Third implication, and this one is going to upset people, is that ancient myths might be less mythical than we thought. Every culture on Earth has flood stories, catastrophic destruction from the sky, gods or cosmic forces reshaping the world in fire and water. We've explained these as memories of local disasters, tsunami stories passed down and exaggerated, volcanic eruptions that seemed apocalyptic to small populations. But what if some of these stories are memories of real global or near-global catastrophes triggered by cosmic events? What if a major cometary passage 10,000 years ago, as the Ice Age was ending, triggered enough volcanic and seismic activity to seem like the world was ending? What if the ancients who built observatories to track comets and planets weren't just astrologers? What if they were tracking real threats? Göbekli Tepe in Turkey, an 11,000-year-old megalithic site, has carvings that some researchers interpret as depicting a comet strike or catastrophic cosmic event. The Younger Dryas impact hypothesis suggests a comet or asteroid airburst 12,800 years ago triggered rapid cooling and megafaunal extinctions. The hypothesis is controversial, the evidence debated, but the idea that cosmic impacts or near misses have shaped human history is not absurd. If electromagnetic effects from comets can trigger geological disasters, then the number of cosmic events capable of affecting civilization increases dramatically. You don't need an impact. You don't even need a close pass. You just need an electrically active object passing through the inner solar system at the wrong time, when Earth's geological systems are primed. Fourth implication is that the future is more uncertain than we thought. Climate change, ecosystem collapse, nuclear war, these are the existential threats we focus on because they're anthropogenic, under our control at least in theory. But cosmic threats are wildcards. Asteroid impacts are recognized hazards. We track near-Earth objects. We develop deflection technologies. That's good. But if electromagnetic comet triggers are real, we have a whole new category of threat that we can't easily defend against. You can't deflect a comet that's not on a collision course. You can't shield Earth's magnetosphere. You can't turn off the piezoelectric properties of the crust. If a bad comet shows up on a bad trajectory at a bad time, we might just have to ride it out and hope our infrastructure holds. Fifth implication, and maybe the most unsettling, is that Earth is part of a larger system. We think of our planet as a closed system, at least geologically. The atmosphere is influenced by the sun, climate varies with orbital cycles, tides are driven by the moon, but the solid Earth does its own thing. Plate tectonics don't care about sunspots. Volcanoes erupt on geological timescales indifferent to cosmic events. That's been the paradigm. But if electromagnetic coupling between cosmic objects, the sun, and Earth's interior is real, then our planet is not closed. It's open. It's influenced by things happening millions of kilometers away. It's part of an electrical circuit that extends across the solar system and potentially beyond. That means Earth's history is not just a story of internal evolution. It's a story of interactions with a dynamic, occasionally violent cosmic environment. Mass extinctions might correlate with more than just asteroid impacts. Volcanic mega-eruptions might have cosmic triggers. Ice ages might be influenced by long-period changes in solar system electromagnetic dynamics. We'd have to rethink planetary history through a wider lens, looking not just at what happened on Earth, but what was happening in space at the same time. Sixth implication is that we need to upgrade our monitoring. Right now, we have decent coverage of seismic activity, okay coverage of volcanic monitoring, good coverage of space weather near Earth, and improving coverage of comet and asteroid tracking. But we don't have integrated systems that look at all of these together in real time, searching for correlations, testing electromagnetic hypotheses. We need a global observatory network that simultaneously monitors the sun, the solar wind, Earth's magnetosphere, ground magnetic fields, seismic activity, and volcanic precursors, all time-stamped and cross-correlated. That's expensive. That requires international cooperation. But if the hypothesis is correct, it could provide early warning of electromagnetically triggered geological events. We might not be able to prevent them, but we could evacuate, prepare, mitigate. Seventh implication, and this is where it gets philosophical, is that the universe is more interconnected than our reductionist science acknowledges. We've spent centuries breaking nature into smaller pieces, studying each piece in isolation, believing that understanding the parts means understanding the whole. That approach has given us incredible power and knowledge, but it's also blinded us to emergent properties, to complex systems where everything affects everything else in non-obvious ways. The solar system is not billiard balls on a table. It's a web of electromagnetic interactions, gravitational influences, plasma dynamics, and feedback loops we're only beginning to map. Earth is not isolated. Life is not separate from cosmos. Everything is embedded in everything else. That's not mysticism. That's just complex systems science applied at the larger scales. If 3I-ATLAS teaches us anything, it should teach us humility. We don't know as much as we think. The universe is weirder and more connected than our textbooks suggest. Anomalies matter. Coincidences are worth investigating. And sometimes, the fringe ideas are fringe only because we haven't looked closely enough to see they're correct. So here we are, late November 2025. An interstellar comet with strange properties has passed the Sun, triggered a solar outburst, and possibly shaken our planet. It's now approaching Earth for a close pass in December. The mainstream denies any connection. The data whispers otherwise. History shows patterns, physics provides mechanisms, and the next act is about to begin. We're living through a test of how well we can see beyond our assumptions, how quickly we can integrate new observations, how bravely we can face implications that challenge our worldview. The universe doesn't care whether we're ready. 3I-ATLAS is coming closer. Earth is waiting. And somewhere between the silence of the establishment and the trembling of the ground, the truth is trying to speak. The only question left is whether we'll have the courage to listen before it's too late, or whether we'll cling to comfortable denial until the shaking starts again, and we're forced to admit that maybe, just maybe, we never understood our place in the cosmos as well as we thought we did. Welcome to the circuit. We've been part of it all along. We just forgot to notice until something came along to remind us. Part 11. The Forgotten Science. There's a name you probably haven't heard. Immanuel Velikovsky. In 1950, he published a book called Worlds in Collision that suggested planets and comets had close encounters in historical times, causing catastrophes recorded in ancient myths. Venus was once a comet ejected from Jupiter, he claimed. It passed near Earth, causing the plagues of Egypt, the parting of the Red Sea, other biblical events. Mars made close approaches that stopped Earth's rotation temporarily. The book was sensational, a bestseller, and absolutely demolished by the scientific establishment. Velikovsky was called a crank, a pseudoscientist, dangerous. His ideas violated celestial mechanics. Planets don't bounce around like billiard balls. The orbits are stable, predictable, governed by gravity alone. The establishment was so offended that they threatened boycotts against the publisher. Academic careers were threatened for anyone who took Velikovsky seriously. He became the poster child for fringe catastrophism, the guy you mention when you want to dismiss someone's crazy theory by association. But here's the thing, Velikovsky got the mechanism wrong, but he wasn't entirely wrong about everything. He predicted Venus would be hot when everyone assumed it was temperate. Confirmed. He predicted it would have a dense atmosphere with hydrocarbon clouds. Partially confirmed it's carbon dioxide but with trace hydrocarbons. He predicted radio emissions from Jupiter. Confirmed before his book was even published, but after he'd submitted the manuscript. He predicted the moon would have remanent magnetism. Confirmed by Apollo samples. He got lucky on some predictions, wrong on others, but his track record wasn't zero. What he understood intuitively was that the solar system might not be as stable and boring as mid-20th century astronomy assumed. The establishment's reaction to Velikovsky created a chilling effect that lasted decades. Any suggestion that cosmic events could cause terrestrial catastrophes became taboo. You couldn't propose it without being labelled a Velikovskyan, which was career poison. The Luis Alvarez asteroid impact hypothesis for dinosaur extinction faced similar resistance when first proposed in 1980. Geologists hated it. The idea that an extraterrestrial event could cause mass extinction violated uniformitarian principles, the idea that Earth's history is shaped by slow, gradual processes. Only after the Chicxulub crater was found and the iridium layer confirmed did the hypothesis become acceptable. Even then, it took years. Now we have another taboo idea, electromagnetic coupling between cosmic objects and Earth's interior causing geological events. It sounds like Velikovsky 2.0, electric universe mysticism, fringe catastrophism. The establishment reflex is to dismiss it reflexively. But what if we're repeating history? What if the reflexive dismissal of uncomfortable ideas is preventing us from seeing a real phenomenon? Part 12. Electromagnetic anomalies. There's actually a longer tradition of electromagnetic geophysics that's been ignored or sidelined. In the 1960s and 70s, researchers explored piezoelectric effects in rocks, earthquake lights, electromagnetic precursors to seismic events. Soviet scientists were particularly active in this area. They documented cases where electromagnetic anomalies preceded earthquakes by hours or days. Animal behavior changes that might be responses to electromagnetic field changes. Lights in the sky before major quakes. This was real research, published in journals, but it never became mainstream in Western geophysics. Why? Partly because the Cold War made Soviet research suspect. Partly because the mechanisms weren't well understood. Partly because it smelled too much like earthquake prediction, which had become unfashionable after several high-profile failures. But the observations remain. Earthquake lights are real. They've been photographed, videoed, documented hundreds of times. They appear as glowing orbs, sheets of light, or streamers in the sky before, during, or after significant earthquakes. The standard explanation is that seismic stress in quartz-rich rocks generates piezoelectric currents, which ionize the air, creating visible plasma. That explanation requires accepting that piezoelectric effects in the crust can be strong enough to ionize air. If stress in rocks from tectonic forces can generate that much voltage, why couldn't externally applied electromagnetic fields generate stress in rocks through the reverse effect? The physics works both ways. It has to. There's also a body of research on solar-terrestrial interactions that's been marginalized. Alexander Chizhevsky, a Russian scientist working in the early 20th century, documented correlations between solar activity cycles and historical events, epidemics, social unrest, even revolutions. He suggested that solar electromagnetic activity affects biological systems, including human nervous systems. His work was suppressed under Stalin. He was sent to a labour camp, but some of his correlations have been replicated. Solar cycle peaks do correlate with increased hospital admissions for cardiovascular events, changes in human reaction times, alterations in accident rates. The mechanisms are debated, but the correlations are statistically significant. If solar electromagnetic activity can affect human biology through poorly understood mechanisms, why couldn't it affect geology through equally poorly understood mechanisms? Both require accepting that electromagnetic fields have effects beyond what we currently model. Both challenge reductionist assumptions. Both have been resisted because they complicate clean, simple theories. The problem with science is that it's done by humans, and humans have cognitive biases. Confirmation bias makes us notice evidence that supports our theories and ignore evidence that contradicts them. Authority bias makes us defer to established experts and prestigious institutions. Paradigm bias makes us reject ideas that don't fit our worldview, even if the evidence is strong. These biases serve us well most of the time. They prevent us from chasing every crazy idea, wasting resources on dead ends, but occasionally they blind us to genuine anomalies that signal something important. 3I-ATLAS is an anomaly, the sunward jet that shouldn't exist, the solar outburst with suspicious timing, the globally synchronized geological response. Each anomaly alone can be explained away. Together they form a pattern. Patterns are how we detect signals in noise. But if you're trained to treat certain patterns as noise because they don't fit your model, you'll never see the signal. You'll keep explaining away the anomalies one by one, never stepping back to see what they're telling you collectively. There's a concept in statistics called the file drawer effect. Studies that find positive results get published. Studies that find nothing get stuffed in a file drawer and forgotten. Over time, the published literature becomes biased toward positive findings, creating a false impression of how strong the evidence is. A similar effect operates in science more broadly. Ideas that fit the paradigm get funded, researched, published, taught. Ideas that don't fit get starved of resources, never properly tested, dismissed as fringe. The result is a literature and knowledge base that's systematically biased toward paradigm-confirming ideas, not because of conspiracy, just because of human nature and institutional inertia. How many observations of electromagnetic precursors to earthquakes are sitting in file drawers because they didn't fit the accepted model? How many times have seismologists noticed strange correlations with solar activity, but didn't publish because it seemed too weird? How many times have astronomers observed cometary behavior that violated standard models but explained it away as instrumentation error or measurement noise? We'll never know. The data is scattered, unpublished, forgotten. Only now, with 3I-ATLAS, do we have a case so blatant, so well documented with modern instruments, that it can't be ignored. This is our file drawer moment, the anomaly that forces everything else out into the light. If the electromagnetic hypothesis is confirmed, if it becomes impossible to deny that cosmic events can trigger geological responses, then we'll have to go back through history and re-examine all the anomalies we dismissed. Cometary passages coinciding with eruptions, solar storms preceding earthquakes, ancient catastrophe myths, Velikovsky's predictions, the Soviet earthquake light research, Chizevsky's solar terrestrial correlations. All of it will need to be reassessed, not because it was all correct, but because some of it might have been pointing at something real that we weren't ready to see. Science advances one funeral at a time, Max Planck supposedly said. The old guard resists paradigm shifts not because they're stupid, but because they've invested careers in the old paradigm. They have expertise, reputation, identity tied up in it. Admitting the paradigm is incomplete feels like admitting their life's work was based on a mistake. That's psychologically difficult. Younger scientists with less invested can adopt new ideas more easily. Eventually, the old guard retires or dies, the new guard takes over, and the paradigm shifts. It's a slow human process. But sometimes, events force the shift faster. Wars, technological breakthroughs, anomalies so large they can't be ignored. 3I-ATLAS might be that anomaly. Not because it's the first hint that electromagnetic effects matter geologically, but because it's the most obvious, the most well-documented, the most impossible to dismiss. If December brings another round of geological activity coinciding with the comet's close approach, if the pattern holds, if predictions based on the electromagnetic models prove accurate, then the paradigm will shift whether the old guard is ready or not. The evidence will force it. And when it does, all the forgotten science, all the dismissed observations, all the fringe ideas that were actually just ahead of their time will suddenly become relevant again. We'll look back at this moment, late 2025, and recognise it as the inflection point. The time when we stopped treating Earth as an isolated rock and started seeing it as part of an electromagnetic web connecting everything in the solar system. The time when we realised the ancients weren't entirely superstitious when they feared comets. The time when we learned that the universe is stranger, more interconnected, more alive with forces we barely understand than we ever imagined. But first, we have to get through December. First, we have to see if the pattern holds. First, we have to overcome our cognitive biases and institutional inertia long enough to actually look at what the data is screaming at us. That's the hard part, not the science, the psychology. Can we admit we might have been wrong? Can we change our minds when the evidence demands it? Can we be scientists in the truest sense, following the data wherever it leads, even if it leads somewhere uncomfortable? We're about to find out. Part 13. The personal stakes. Let's bring this down to ground level. Forget the cosmic scales, the theoretical mechanisms, the scientific debates. Let's talk about what this means for you, personally, if the hypothesis is correct. Because science is abstract until it's not, until it's your house shaking, your city evacuating, your food supply disrupted, your power grid failing, then it becomes very real, very fast. If you live in Indonesia, you've already felt this. The November eruptions weren't just data points. They were ash falling on your roof, animals dying, skies turning dark. If Halley-Gubby's eruption was electromagnetically triggered, and if 3I-ATLAS triggers more activity in December, then you're potentially looking at multiple eruptions in one of the most volcanically active regions on Earth within a 2-month span. That's not academic. That's survival. Indonesia has over 100 active volcanoes and 270 million people, many living within hazard zones because the volcanic soil is fertile and land is limited. A typical volcanic crisis sees tens of thousands evacuated for weeks or months. Multiple simultaneous eruptions could see millions displaced. Where do they go? Refugee camps strain under single disaster loads. Multiple disasters simultaneously would overwhelm response capacity. Food, water, shelter, medical care, all become scarce. This isn't speculation. This is emergency management math. If you live in Japan, you're watching nervously. The country sits on the ring of fire, has over 100 active volcanoes, and is still traumatized by the 2011 Fukushima disaster, where an earthquake and tsunami caused a nuclear meltdown. If electromagnetically triggered seismicity is real, and if the December comet passage triggers a major quake in the wrong place, Japan could face another compound disaster. Earthquake damages infrastructure, tsunami if it's offshore. Nuclear plants have been upgraded since Fukushima, but are they upgraded against unexpectedly timed quakes? The psychological impact alone would be immense. Japan has earthquake preparedness drilled into its culture, but preparation is built around statistical risk models. If those models don't account for cosmic triggers, the preparation might not match the actual threat. If you live on the US West Coast, you've been waiting for the big one for decades. The Cascadia subduction zone offshore from Northern California through Oregon to Washington hasn't ruptured since 1700. It's overdue in human timescales, though geological timescales are more forgiving. When it goes, it will produce a magnitude 9 earthquake and tsunami. Tens of thousands dead, hundreds of billions in damage, regional economy destroyed for years. We know it's coming. We don't know when. Could an electromagnetic trigger push it over the edge if it's close to critical? Maybe. If the December comet passage coincides with Cascadia rupturing, was it coincidence or cause? We'll never know for certain, but you'll care a lot less about causation when you're dealing with the aftermath. If you live near Yellowstone, you joke about the supervolcano but secretly worry. Yellowstone's caldera last erupted 640,000 years ago. It's had smaller eruptions since, but the big one is theoretically possible. The probability in any given year is 1 in 730,000. Low, but not zero. If electromagnetic triggers can affect volcanic systems, and if Yellowstone happens to be closer to critical than we think, then even a small push from a comet could matter. A Yellowstone supereruption would bury the western US under ash, disrupt global climate for years, potentially kill millions through starvation and societal collapse. This is worst-case thinking, the kind of scenario you don't really believe will happen to you. But somebody said that about Pompeii in 79 AD. Somebody said that about Tambora in 1815. Somebody always thinks it won't happen to them, right up until it does. If you live anywhere, even far from volcanic or seismic zones, you're still connected to the system. Global food supply depends on stable agriculture. Major eruptions inject sulfur into the stratosphere, reflecting sunlight, cooling temperatures. The year without a summer in 1816 following Tambora caused crop failures in Europe and North America. People starved. Social unrest increased. Multiple simultaneous eruptions in 2025 to 2026 could cause similar effects. Your grocery store shelves empty not because your region had a disaster, but because regions that grow your food had disasters. This is how globalization works. Everything is connected. Disruption anywhere propagates everywhere. If you work in critical infrastructure, power, water, communications, transportation, you should be paying attention. Geomagnetic storms induce currents in long conductors, power lines, pipelines. We design systems to handle typical solar storm levels. But if comet passages can amplify geomagnetic disturbances, if the December event produces stronger induced currents than expected, transformers could be damaged. Power grids could fail. We saw a preview of this in 1989 with the Quebec blackout. That was a 9-hour outage affecting 6 million people from a strong but not unprecedented geomagnetic storm. A stronger storm affecting a larger area could be far worse. Weeks without power in winter in northern latitudes means people freeze. Hospitals lose backup power, water treatment fails, society frays within days. If you're in government or emergency management, you're caught between a rock and a hard place. If you warn people about potential cosmic triggers for geological disasters, you risk panic, economic disruption, and looking foolish if nothing happens. If you don't warn people and something does happen, you're criminally negligent. The calculus is brutal. The safe bureaucratic choice is to say nothing, prepare quietly, and respond after the fact if necessary. That minimizes political risk for officials, but it maximizes risk for populations who could be preparing individually if they knew. This is the tragedy of institutional incentives. What's safe for the institution is not always safe for the people. Part 14. Cosmic Triggers. If you're a scientist, you're facing the choice between career safety and intellectual honesty. Publishing a paper suggesting cosmic triggers for geology will get you laughed at by half your colleagues and maybe blackballed from grants and conferences. But if the hypothesis is correct and you stayed silent to protect your career, you'll have to live with knowing you could have contributed to understanding that might have saved lives. That's a heavy weight. Not every scientist is in a position to take that risk. Junior researchers, people without tenure, those from marginalised backgrounds who already face extra scrutiny, they can't afford to champion fringe ideas. The cost is too high. But someone has to be first. Someone has to stick their neck out. The question is who has enough security and courage to do it. If you're just a regular person trying to live your life, you're probably thinking this all sounds insane, and why should you care about some comet millions of kilometres away when you have bills to pay and kids to feed? That's fair. Most of the time, cosmic events don't matter to daily life. The sun rises, the Earth spins, the planets orbit, and none of it affects whether you get to work on time. But occasionally, rarely, the cosmic and the mundane intersect. A solar flare knocks out GPS and you can't navigate. An earthquake hits and your house collapses. A volcano erupts and ash ruins your crops. When it happens, the scale doesn't matter. The mechanism doesn't matter. What matters is that your life just got destroyed by something you had no control over and barely understood. That's the stakes. Not abstractions, not scientific curiosity, but lives, homes, communities, civilization. If the electromagnetic hypothesis is wrong, if 3I-ATLAS passes in December and nothing happens, then we breathe a sigh of relief, and this becomes a footnote. A moment when we thought the sky was falling, but it wasn't. If the hypothesis is correct and we see another round of geological activity, then everything changes. We have to rethink planetary risk. We have to upgrade monitoring and early warning systems. We have to educate populations about a threat they didn't know existed. We have to fund research into mechanisms we've ignored. All of that takes time, money, political will. And in the meantime, people are vulnerable. The cosmic doesn't care about politics, economics, or human readiness. 3I-ATLAS is following its trajectory, indifferent to our debates, our fears, our preparations, or lack thereof. It's going to pass Earth in late December. It's going to interact with our magnetosphere in whatever way its electromagnetic properties dictate. And if that interaction stresses the crust, if magma chambers pressurize, if faults slip, then people will die. Not because we didn't have the science to understand what was happening, but because we didn't have the courage to look at the science honestly and act on it. That's on us. Not the comet. Us. The comet is just doing what comets do. We're the ones who choose whether to pay attention, whether to prepare, whether to take seriously the possibility that our models might be incomplete and our planet might be more vulnerable than we thought. December is coming. The comet is coming. And somewhere, in some community near some volcano or some fault, People are going about their lives unaware that the ground beneath them might be about to shake, not because of blind geological chance, but because something from the stars reached down and touched them. They deserve better than our silence. They deserve the truth, however uncomfortable, however uncertain, however paradigm-shattering it might be. The question is whether we're brave enough to give it to them. Step back. Look at the whole picture. Not just 3I-ATLAS, not just the November eruptions, not just the December approach. Look at everything that's been building over the last few years. The pattern is bigger than one comet. Solar Cycle 25 started in December 2019. We're now in the ramp-up phase towards solar maximum, expected around 2025. Solar activity has been stronger than predicted. Sunspot numbers are running ahead of forecast models. We've already seen several X-class flares, the strongest category. Space weather forecasters keep revising their predictions upward. The sun is more active than it's supposed to be at this point in the cycle. Why? Internal solar dynamics, says the standard answer. Natural variation within the cycle. But what if external factors are influencing it? The number of interstellar objects we've detected has jumped. Before 2017, we'd never confirmed an interstellar visitor. Then came Oumuamua, weird elongated object that accelerated without visible outgassing. Then 2019 saw 2E/Borisov, clearly a comet but with unusual composition. Now 3I-ATLAS, also anomalous. 3 confirmed interstellar objects in 8 years after finding 0 in all of previous human history. Either we just got better at detection, which is true, our surveys improved, or the rate of interstellar visitors passing through the inner solar system has increased. Why would the rate increase? One possibility is that our solar system is passing through a denser region of the interstellar medium, a cloud of gas and dust that funnels more objects our way. Another possibility is that something disturbed the Oort cloud, the distant shell of comets surrounding our solar system, causing an increase in objects getting perturbed onto inner system trajectories. Part 15. The message in the pattern. Geological activity globally has been elevated. The United States Geological Survey tracks significant earthquakes, magnitude 6 and above. The rate fluctuates year to year, but the 2020 to 2025 period has been active. Multiple magnitude 7 events, several destructive quakes in populated areas. Volcanic activity has also been notable. Iceland's ongoing eruptions near Grindavik, which started in 2023 and have displaced a town. Taal in the Philippines showing unrest. Etna and Stromboli in Italy continuously active. Kilauea in Hawaii. Reykjanes Peninsula. Multiple systems showing signs of unrest or eruption in a relatively short time frame. Is this unusual? In isolation, no. Geological activity is always happening somewhere. But the clustering, the sense that multiple systems are acting up simultaneously, that feels different. Felt, past tense, until November 2025 when it became undeniable. Climate patterns have been weird. Record heat years back to back. Atlantic meridional overturning circulation. The ocean current system that includes the Gulf Stream, showing signs of weakening. Ice sheets melting faster than models predicted. Jet stream patterns becoming more meridional, loopy, causing extreme weather. Standard climate science attributes this to anthropogenic greenhouse gas emissions and positive feedbacks. All true. But could there also be external forcing? Could increased cosmic ray flux from higher solar activity be affecting cloud formation, which affects albedo, which affects temperature? The cosmic ray hypothesis for climate has been explored and remains controversial. The correlation between solar activity and climate exists, but the mechanism is debated and the effect size questioned. Still, dismissing it entirely might be premature if electromagnetic coupling between Sun and Earth is stronger than currently modelled. Now layer on 3I-ATLAS, an electrically anomalous interstellar object passing through during a solar maximum phase that's running hot, triggering or coinciding with a major solar outburst, followed by globally synchronized geological unrest, approaching Earth for a close pass during a time when geological and space weather systems are already elevated. Each piece individually is explainable. Together the pattern suggests we're in a period of heightened solar system dynamism. The circuit is running hot. The electromagnetic environment is disturbed. Earth, as part of that circuit, is responding. The message in the pattern is that we live in a dynamic, interconnected system, not a stable, isolated one. The solar system isn't a peaceful clockwork. It's a noisy, chaotic electromagnetic environment where disturbances propagate in complex ways. Earth isn't a closed geological system evolving according to internal rules alone. It's coupled to solar activity, to cosmic ray flux, to magnetic field interactions, to passing objects, all of which can modulate or trigger geological processes. Life on Earth isn't separate from this cosmic environment. It evolved within it, adapted to it, is shaped by it in ways we're only beginning to understand. Evolution, for instance, is driven by mutation. Cosmic rays cause mutations. The rate of cosmic ray flux reaching Earth's surface depends on solar activity and Earth's magnetic field strength. When the solar wind is weak or Earth's magnetic field is weak, more cosmic rays penetrate, more mutations occur, evolution accelerates. Conversely, during periods of strong solar activity and strong magnetic field, cosmic ray flux is lower, mutation rates decrease, evolution slows. This is called the cosmic ray mutation hypothesis, and while it's speculative, it's based on solid physics. If true, then the rate of biological evolution on Earth is coupled to solar system electromagnetic dynamics. We're not just products of Earth, we're products of the cosmos. Human civilization, too, might be more coupled to cosmic conditions than we realize. Chizhevsky, mentioned earlier, documented correlations between solar cycles and historical events. War, revolution, social unrest cluster during solar maximum, peace, stability, cultural flowering cluster during solar minimum. The proposed mechanism is that solar electromagnetic activity affects human neurological and psychological states, making people more irritable, impulsive, aggressive during high solar activity. The evidence is correlational, not causal, but the correlations are statistically significant over centuries of data. If solar activity can affect human behavior, then history is not just a product of human decisions and societal forces. It's also influenced by cosmic rhythms we're unconsciously responding to. This is not astrology. Astrology posits that planetary positions at your birth determine your personality and fate through some mystical influence. That's nonsense. But the idea that solar activity, space weather, cosmic ray flux, and electromagnetic field fluctuations affect biological and psychological systems through known physical mechanisms, that's science. Controversial science, marginalized science, but science nonetheless. And if those effects are real, then we need to incorporate them into our understanding of Earth history, human history, even current events. 3I-ATLAS, in this view, is not an isolated anomaly. It's part of a larger pattern of elevated solar system activity that we're experiencing in the early 21st century. The comet is a tracer, a visible symptom of dynamics that have been building. Its electromagnetic properties make it a particularly strong perturbation, but the system was already primed. Solar cycle 25 is stronger than expected. Geological systems are stressed. Human civilization is stressed politically, economically, socially. All of these stresses might be interconnected, all symptoms of a solar system that's currently in a more dynamic, energetic state than it has been for decades or centuries. If true, then 3I-ATLAS is not a one-off threat. It's a preview. The early 21st century might be remembered as the time when cosmic factors reasserted themselves in human affairs after being ignored or forgotten for centuries. We built modern civilization during a period of relatively calm solar activity, the so-called modern maximum from the 1940s to early 2000s, when solar activity was the highest in centuries. We got used to that. We designed systems assuming it would continue. Now solar activity is transitioning, possibly entering a grand solar minimum, like the Maunder minimum of the 1600s, or possibly shifting to a different mode we don't yet understand. Either way, the conditions are changing. Earth is responding, civilization is vulnerable. The message in the pattern is simple but uncomfortable. We are not separate from the cosmos. We are embedded in it, affected by it, vulnerable to it. The stability we've enjoyed for the last few centuries, the predictability of climate and geology that allowed civilization to flourish, that's not guaranteed. It's contingent on cosmic conditions remaining favourable, and right now the signs suggest those conditions are shifting. 3I-ATLAS is a messenger, telling us to wake up, pay attention, stop pretending we're immune to forces beyond our planet. Whether we listen to that message, whether we adjust our thinking and our preparations accordingly, that's up to us. But the message is being delivered whether we want to hear it or not. The only question is whether we'll understand it in time.